Okay, here we're going to look at the conditions for static equilibrium. Now, by static equilibrium, we mean that an object that is at rest will remain at rest. That means there can be no net external forces in any direction, and there can be no net external torques, so that the object will not translate nor will it rotate. So our condition will be that the sum of all of the forces in the x direction must add up to 0. Sum of all of the forces acting in the y direction will add up to 0. And the net external torques about some axis, and we're allowed to pick whatever axis we want because we want it in static equilibrium around all axes. So we get to pick one. Generally speaking, you want to pick one where there are unknown forces acting, so those forces will not exert torques. That just simplifies the math. So we can consider this example right here where we have essentially a scaffolding being supported by two ropes at either end that are attached to an upper support, say a ceiling, and we've got a person standing at a given distance from one end of the scaffolding. And what we wish to do is find what are the conditions for this to be in static equilibrium. And that is the sum of all the forces and the sum of all the torques must be 0. So, since we have to worry about rotation, we need to worry about not only the magnitude, but also the direction and the point of application of each of the forces. We have the two ropes exerting upward tensions on opposite ends of this platform. And then we have the weight of the platform, and that will act through the center of gravity or the center of mass of the platform, so that acts at the midpoint. And then we have the woman standing right here, and her weight will exert a normal force downward on the platform, and those are all of the forces. So all of the forces in the vertical direction have to add up to 0, so the two tensions up and the two weights down must add up to 0. There are no horizontal forces to worry about. We're going to take this end right here to be our axis of rotation to calculate the torques, which have to add up to 0. The torques will be the tension on the opposite end is exerting a counterclockwise torque, so that is positive. The weight of the woman is exerting a clockwise torque, so that is negative, and the weight of the platform is also exerting a clockwise torque, so that will also be negative. So here we have her weight exerts as a lever arm of 1.5 meters, her distance from the axis of rotation, and the weight of the platform has a lever arm half the length of the lever of the platform, hence the L over 2. This basically gives us two equations for two unknowns. The two unknowns are the two tensions. Notice, because we picked this end of the platform to be our axis of rotation, the only unknown in the second equation is this tension, the tension on the opposite side. So the torque equation can be solved for T2. We can then plug that number into the first equation to get T1. We would get the exact same answer, for example, if we picked the center of mass of the platform, but then the torque equation would have two unknowns in it. We'd have a set of equations, two equations and two unknowns. If you solve them, you get the exact same answer. It's just you'd have a little more work to do. And if you punch the numbers out with the two equations and two unknowns, these are our two answers. Now, another kind of static equilibrium problem could be the platform, if you will, rather than horizontal, we can put it at an angle and make it a ladder leaning up against a building. And here we have a person partway up the ladder. Here we're also going to say the ladder itself is not of uniform density, if you will. Its center of mass is down low. So we have the mass of the ladder is given. Its location for its center of mass is only a third of the way up. We're given its length, and we're given where the ladder touches the wall, 9.3 meters up. We're given the mass of the firefighter, and we know where the firefighter is halfway up. And what we wish to do is find the forces at both ends of the ladder. Now, here we're going to assume that the surface up here on the wall is frictionless, and we'll see why we make that later. So what we want to do is find the forces acting on the ground right here. Now there has to be a normal force up, and there here also has to be a friction. The friction is going to oppose the bottom of the ladder from sliding out from the wall, so that means friction will act inward towards the wall. We have the weight of the firefighter halfway up, and the weight of the ladder, which is at its center of gravity or its center of mass, which is given as a third of the way up. And then we have the normal force from the wall pushing directly outward horizontally. So these are all the forces acting on the ladder. And then we need to pick our axis of rotation. Again, we can pick any point on the ladder to use as our axis of rotation because we don't want the ladder to be rotating at all. Easiest point to pick is the base right here. So then two of our unknown forces, the normal force from the ground and the frictional force from the ground, will act at the axis of rotation. They will not exert torques, which simply means the torque equation will only have one unknown, the normal force from the wall. So that'll simplify our math. And again, all of the forces acting vertically have to add up to zero. Here we do have horizontal forces, so all the horizontal forces have to add up to zero. So again, what we can do is set up our equations. The sum of the vertical forces and the sum of the horizontal forces have to add up to zero. And then we're going to pick the base of our ladder as our origin for our axis of rotation and say the torques around that point have to add up to zero. And here the way we're going to calculate our torques is to say torque is basically the force times the lever arm. And the lever arm is basically the distance between the axis of rotation and the line of action of the force. So for an example, the force of the wall, notice that is a clockwise torque, and its lever arm is the distance from where the wall touches the ladder and the ground, or H. The firefighter is halfway up. So its lever arm is this distance, and we call A the distance from the base of the ladder to the wall. That's halfway from the base of the ladder to the wall. And the weight of the ladder, that's a third of the way. So all we need to do is calculate what A is, and since we know H and we know L, and this is a right triangle, we can calculate A, and therefore we can get A over 2 and A over 3. So those are the lever arms for the two. These are both counterclockwise torques. And that gives us the third equation. And notice here we have three equations, and there are three unknowns. The unknowns are the force that the wall exerts, the frictional force, and this tells us that they have to be equal. This is the normal force must equal all of the weights. The ground has to support all of the weights. This right here, the torque, will give us the force of the wall, and we also know the force of the wall has to equal the frictional force, so that answers all of the problems. So here are our answers. By the way, this is also a worked example in your textbook around page 335. Now, notice we assumed the wall was frictionless. Why did we have to make that assumption? Well, we have a set of requirements. We have that the net force in two different directions has to add up to zero, and the net torque around the one axis has to add up to zero. That gives us three requirements, and we can write each of those requirements in the form of an equation. So that gives us three equations. Three equations can be used to define only three unknowns. The three unknowns are the normal force that the ground exerts up on the wall. We need that to counterbalance gravity. We need friction on the ground to stop the ladder from sliding along the ground. And we also need the normal force in the wall to hold the ladder up. Those are the three forces that we need. Technically, we don't need any friction, so therefore we assumed that there were none. If we did put it in, we'd have three equations and four unknowns, and we wouldn't have a solution. We would need to have some new constraint in order to apply a fourth equation to figure out what the friction would be. And the key thing is we are assuming all of the objects are rigid and do not bend. And that's the one assumption that we do have to drop. The ladder, that turns out, has to bend or sag or somehow be flexible. We can see that by considering the following problem. Here we have a guy we're going to call Strongman Sam. He's going to support a 10-pound telephone book with a rope held vertically, in which case the tension on each side of the rope will be 5 pounds. So the two 5-pound forces will support the 10-pound weight. Now he's going to take and try to pull the rope so that it is horizontal. The question is, how hard does he have to pull to make the rope go horizontal? So think about that for a moment. If you think about it, you realize he actually can't do that. he actually has to pull incredibly hard because the rope can't be held horizontally. It has to sag. Namely, the rope has to have some component pointing upward, totaling 10 pounds. Now, if he does exert a force of about 1,000,000 pounds, relatively speaking, that 10-pound upward force will be very small compared to the 1,000,000 pound horizontal force. So it may look horizontal, but it can't be. The rope must sag. Likewise, the ladder here has to bend. In effect, the assumption we had to drop that we did assume before, namely that this was a right triangle, and the ladder was therefore the hypotenuse of a right triangle, that allowed us to calculate A. We can't assume that because the ladder has to bend. Now this then brings us to the strength of materials and their elasticity, and that's a topic we're just not going to cover. But that is how you would handle there being friction. We're going to simplify the problem by assuming the ladder is rigid and one of the surfaces will be frictionless. Now we can consider another related problem, and that is a boom supporting a weight. In this case, it's a safe. And what we want to do is calculate what is the tension on this cable that is supporting the beam and the weight that we have here, the safe. We are given the weight of the safe, we're given the weight of the boom, we're given the distance A from the hinge to the cable, and we wish to find basically the tension. And here we're going to use the hinge will exert two forces, an upward force and an outward force, or if you will, it's going to exert a force at some angle, and we're going to break it into two components, the X and the Y component. We have the rope pulling down. Again, everything's in static equilibrium, so here the tension on the rope will in fact equal the weight of the safe. And what we wish to find is what is the tension on the cable up here. And the beam also does have some weight, and its weight will act through its center. So again, we're going to set up our equations. The sum of the forces in the X direction have to add up to 0, which means the outward force from the hinge must basically equal the tension on the cable. Some of the forces in the Y direction have to add up to 0, which means the upward force from the hinge has to equal the total weight pulling down. And now we're going to pick the hinge in order to simplify our math, so the only unknown that will exert a torque, will be the tension on the cable. And going back right here, this distance A will be the lever arm that the tension exerts relative to this hinge, and that is a counterclockwise torque. The weight of the boom and the weight of the safe both exert clockwise torques. And this distance right here, which is the length of the cable, which we are given, is the lever arm for the weight of the safe, because that arcs straight down. The line of action is straight down. The distance from the hinge to the line of action is this distance B right here. And the weight of the beam is halfway point. So those are our tensions, two torques, and this gives us an equation we can then solve. These are, again, three equations for three unknowns. We're only asked to find the tension on the cable, but we could use the first two equations also to find the forces from the hinge. Here are our solutions. Tension that we're asked to find is about 6,000 newtons. We could also find the two components of the force from the hinge. Those, of course, can be combined to give us the magnitude and direction of the force from the hinge. And again, this is a worked example in the textbook around page 334.